It dissolves. What does that mean?
It's broken down.
Into what?
Separate.
We're going to break it down into the separate sodiums and chlorines. And they're carrying their positive charge. Now think about that for a second. That charged piece, the salt, puts into water, and then we can break it up into chlorines, sodiums, that are now free. What's the majority of our body? Water. Anybody in here not eat? I love to eat. Okay? Every time you eat, usually in some way, you're taking in salts. Does that make sense? And depending on what you eat, you could be taking in the lipids and you could be taking in the proteins. It becomes important in the body for these particles, these salts that we take in to break apart. That we have them in this chlorine, the magnesium, the sodium, the potassium charged particles that they become. Okay, is everybody following me? All right, that becomes extremely important. So that tells me that throughout my body, these charged particles, these positives and these negatives, are flying around. You're charged. Ionic bonding is going to be probably the most important bond we deal with. Other ones, yeah, sure, they're great, they're good, okay? But they're just, in my world, secondary. When we talk about covalent bonding, well, if something is co, what are you doing? You're sharing, you're working together. So with covalent bonding, that's what happens. When the outer shell is not full of electrons, it simply pairs up with either another element of itself or something else, and they share their electrons. And when they do that, they can form bonds, and they're called covalent bonds. And we can have a single covalent bond, double covalent bond. Now, when these bonds begin to form, these bonds can be rather interesting, all right, because we have what's called either polar or non-polar covalent. When we have non-polar, those electrons are being shared in the outer shell, okay? They're just simply flying around both of those elements equally. For example, hydrogen, number 1 on the periodic table, tells me in this outer shell, this first shell, there's only 1 electron. Well, guess what? This hydrogen right here in this first shell only has 1 electron. Hydrogen and hydrogen form together very quickly. And they have this thing where we've got an H, and now these electrons are flying around both of them equally. Oxygen on the periodic table, when we hear the term oxygen, what do you think of? O what? O2. Why do you think it's called O2? Because one oxygen quickly combines with another one, and they share their electrons. Does that make sense? Now the one that is, there's a substance on our planet that it's the only substance that will exist in all three states. What are the three states? Solid, liquid, and a gas. There's only one substance that exists in all three forms. What is it? Water. H2O. My upside down Mickey Mouse. Because I got a great big huge oxygen, and then I got tiny little hydrogens. Does it look like everybody's kind of equal? No. This is a polar covalent bond. Because oxygen, hydrogen's only got one electron, one electron. Oxygen in its outer shell has 6. By combining the hydrogen and the hydrogen, we now have each of the outer shells full. Is that correct? But oxygen's way bigger, okay, and therefore requires more of those electrons than the hydrogens do. So it's a little bit negative. These have a little bit of a positive electronegativity. All right, is everybody following me? And because of the way that the hydrogens form or bind to the oxygen, basically the bond angle, which is, I want to say 109, but don't quote me on that, for the bond angle, that makes it unique. It is the only substance on the face of the planet that can exist in a solid, a liquid, and a gas. There's no other substance on the face of the planet that can do that. Take a break. Come back at 12:30.